And welcome to the folks who are online. We're getting a little bit of a late start today because of new features of YouTube, which I'll have to figure out for next week. That's one problem with this service is you never know when it's going to change. You only find out when you go to set it up. But speaking of changes, we're going to change gears a bit today with our third lecture. This is today's lecture on probability and Bayes' rule. In some ways, is going to seem like a bit of an aside from everything else that we're covering in the course, from our first two classes on types of variables and data and methods of sampling to the rest of our classes that are going to be more on inference and hypothesis testing. But it's something that is important to cover, I think, early in the course, because it's going to get you up to speed on probability in particular. The parts about Bayes' rule are a bit standalone. You won't need to apply Bayes' rule for other aspects of the course, so that part it won't be sort of sequentially building on, but the aspects of probability you need to understand in order to understand how we do inference and how to do some of the calculations that we're going to do in the rest of the course. So I'm going to cover probability in the context of diagnostic tests because I'm a biostatistician and this is a key application of probability into Bayes' rule. But it is applicable to a number of other topics, essentially anything where you're interested in the probability of something happening based on some other pieces of information that you have. But it's also important, I think, for any professional in public health just to be able to understand when you read news reports and articles about the effectiveness of screening tests, and also as patients ourselves. So the key concepts that we're going to cover relating to diagnostic tests are sensitivity and specificity, positive predictive value and negative predictive value, and how these relate to the prevalence of a disease in the population. And in order to understand these things, we're going to introduce properties of probability and of conditional probability and describe to you Bayes' theorem and its application to screening tests. And we're moving into chapter 2 of your textbook today. I'm going to start with an example that will give you an idea of how well you already understand these concepts of conditional probability and their application to screening tests. And I'm going to make you answer, so pay attention. This is a hypothetical screening test for, let's say, for cancer. And in this example, this screening test is correctly positive for 100% of cancer patients. That means that if you have cancer, it will not miss it. It is guaranteed to give you a positive test if you have cancer. So it's very good in that respect. Now, let's say we go and apply this test in a population where the prevalence of cancer is 5 per 1,000 people per year. That's a pretty high prevalence. Now, if we apply this test to that population, what is the probability that an individual testing positive has cancer? So you're in this population. Before you step into the test, you have a 5 in 1,000 chance of having cancer. You get a positive test. What does it tell you about your probability of having cancer, and how worried would you be? Yep. 100%. 100%. So you'd be 100% worried. I see a couple nodding heads. Is there anyone who wouldn't necessarily be worried? Is everyone worried? I'm not necessarily worried. Why am I not worried? What's that?
That's positive?
No, I tested positive. I tested positive, but I'm still skeptical. Yep.
Still have 5 in 1,000 chance of having it.
You still have a 5 in 1,000 chance of having it. Why is that?
That's prevalent.
That's your probability of having it before the test. After you receive a positive test, your probability could be different. We've heard one person say that your probability after receiving the positive test is 100%. I don't necessarily agree with that, but it could be different than 5 in 1,000. If the test is worth anything, it should be higher than 5 in 1,000 after you test positively. But you do a good job of bringing in the fact that the prevalence matters. Any other ideas? So let's just suppose now, this is a sort of a dummy example here. Let's suppose that this screening test is just, hi Tony. Let's suppose that this screening test, all it is the doctor goes into a back room and comes out with a sheet of paper that says yes every time. You don't know what's going on, but that's what's going on. It just, the doctor always says yes. Does that meet this first requirement? That the screening test is correctly positive for 100% of cancer patients?
Yes.
It is. So this completely useless test that just says yes for everyone meets that first requirement. So that's why, without more information, I'm not necessarily worried about that positive test. If I don't trust my doctor and I don't know anything else about this test. Because what I didn't tell you, I told you about its performance in that 5 out of 1,000, and it's very, very good. But I didn't tell you anything about its performance on those other 9,995 healthy people, and that matters. Right? It matters not only that it performs on the people who have the disease, but it matters that it performs accurately on those who do not. And going into that exam, I know that I am most likely do not have cancer. So I know that that test had better have decent accuracy on people who do not have cancer in order for me to be worried when I get a positive test. So this test has 100% accuracy on people with cancer and 0% accuracy on people without cancer. Terrible test. It's a terrible test, but this is not a totally hypothetical example. Well, it is a hypothetical example, but the lessons from it carry to real-world screening tests. So in order to, that question that I asked you, just to give you a bit of a preview of as we get on, that question that I asked you of, if I receive a positive test, should I be worried? I'm asking you about what we call the positive predictive value. That is, if I get a positive test, how good is that predicting that I actually have the disease? So in an ideal world, these tests would just be 100% accurate. So if you get a positive test, you know you have the disease. If you get a negative test, you know you do not. But in reality, that's not the case. And there are very few tests that do not make mistakes, especially cheap and easy tests that can be applied to millions of people in the general population. They tend to make mistakes. They make two types of mistakes. they call false positives. That's when you get a positive test and it's wrong. And false negatives, when you get a negative test and it's wrong. 2 types of mistakes. And that performance depends not only on characteristics of the test, but the overall performance depends also on the population it is applied to. You can imagine like a test like this that is 100% accurate on patients, on people with cancer. It performs well if you apply it to a population where almost everyone has cancer, and it performs poorly if you apply it to a population where very few people have cancer. So in order to assess these properties of a test, we apply it to compare it to what is called a gold standard, which is some highly accurate but expensive or invasive test. So in the case of cancer, this would mean like biopsies, additional types of imaging to give more direct evidence of the existence of cancer than a screening test, which would be things like mammography, prostate-specific antigen, and other sort of cheap, quick tests for cancer. Okay, a still hypothetical, but slightly more realistic example. This is an example of a screening test for chlamydia being applied to 2 different populations. The one is a sexually transmitted disease clinic. I'm used to calling this infection, not disease, but there we have it. I've also put the paper that this came from. There is an article here, and I believe I posted it to Blackboard. So this is one where patients are coming in because they already suspect that they have an infection. And so there's a higher prevalence of 30%. And then the second population is in a private practice where people are just getting general screening. They don't suspect an infection, so the prevalence is lower in this private practice at 3%. So, but applying the same screening test. It's exactly the same test being applied to these 2 populations. And this test, it's a PCR test for some product of the chlamydia bacteria, and we are seeing here 2x2 plots where one is the truth from this gold standard, whether there is whether the patient has chlamydia or not, and the other is the result of the test, whether it is positive or negative. And among the positive groups here, the positive group, we have an accuracy of 294 out of 300. I don't know what that is. It's pretty good though, something close to 99%. And in the negative group, it's 679 out of 700. Also pretty good. That's, I don't know, 98% or something like that accurate. But now we're calculating using this 2x2 table, this so-called positive predictive value and negative predictive value. And the positive predictive value is how does it perform, or given that you have a positive test, what is the probability of being in fact positive? And that is 294 out of 315, 93%. And the negative predictive value is even better. That is, if you receive a negative test, you can be pretty confident, 99% confident, that you do not have chlamydia. So this is an example of that. It came up a little bit during the questions about, like, your probability of having the disease before testing and after testing. So before, everyone has a 30% chance of having the infection with no other information. Overall, your probability is 30%. But after you receive the test, if you get a positive test, you have a 93% chance of having the infection, only 7% of not having it. And if you receive a negative test, you have only a 1% probability of having the infection and a 99% probability of not. So conditional on the outcome of your test, your probability of having the infection has changed. It depends on whether you received a positive or negative test. And how it changes, though, depends on this prevalence. So in the private practice, with only 3% prevalence, you come out either with a positive predictive value of only 50%. So it's quite a bit worse. Now, if you receive a positive test, there's only a 50% chance that you have the infection. Whereas the negative predictive value is very, very good. It's approaching 100%. This is like a really, I think, initially unintuitive idea for most people, but a really important concept, that when you have uncertainty in the performance of any kind of prediction, the knowledge that you have afterwards depends on the knowledge that you have beforehand. So if going into the test, there's a very small probability that a patient truly has the infection, then coming out of the test, it's going to be raised some, but not as high as if they had had a higher prior probability going into the test. And this is why some diagnostic screening tests, like mammographies, like PSAs, are approved for certain higher risk populations and not approved for lower risk populations, because the performance is not good enough when applied to really low prevalence populations. They have a high false positive rate in these low prevalence populations, or alternatively, a low positive predictive value. So this test, in this example, even though it has very good accuracy on positive cases and on negative cases, something like 99%, that positive predictive value in the general population is not great. It's, I mean, 50%, it's certainly not useless. You went in with a 3% chance of having this infection and came out with a 50% chance, certainly enough of a difference to justify like a follow-up gold standard test. But this physician should certainly be counseling their patients that there's still a pretty good chance, like an even chance, that this is a false positive. Any questions about this? All right. So now you have a couple of examples. I'm going to get into this a little bit more. Starting with a couple of definitions. First, of an event, which is any measurable and definite outcome, something that both we can measure and we can write down those possible outcomes. So such as an individual has a chlamydia infection, yes or no, talking about one individual and they either do or do not have an infection. That is an event. Probability is the rate of an event for some very large number of observations. This is only one definition of probability, but it's the one that we're going to use. So if we look at a very large number of people, the frequency of chlamydia infections, so the frequency of those yes events is the probability of having chlamydia. Sensitivity and specificity are what we call intrinsic properties of a test. So these have to do with how, like the chemistry of the test, just the workings of how this test operates. Where sensitivity is the probability of a positive test for individuals with disease, that is its accuracy on the positive cases, and specificity is the probability of a negative test for individuals without the disease, or in other words, its accuracy on negative cases or negative controls, people without the thing that is being tested for. These have nothing to do with the population. These are only properties of the test, right? Because I'm telling you that sensitivity is a property only on individuals with the disease, and specificity is a property that applies only to individuals without the disease. So it does not matter what the prevalence in the population is. This is only an intrinsic property of the test. So that is sensitivity and specificity, and they are properties of the test when applied to people with or without the disease being tested. These apply also not only to screening tests, but to anything where you're making predictions. If you talk about predictive modeling or machine learning, any of these things, sensitivity and specificity have the same meaning. You have to pick like one outcome that is your event and one is your non-event. And sensitivity is your accuracy for the events, and specificity is your accuracy for the non-events. So in other words, something that is highly sensitive means that for the events, it predicts them accurately. So that first test on the very first slide, that was a highly sensitive test. It never misses a case of cancer. So it's highly sensitive. Whereas specificity is that probability of a negative test, or the performance on non-events. So this tells you one way to think about it is its performance on the negative tests. Another way to think of it would be how contaminated your true positive predictions are going to be with false positive predictions. A test that is highly specific is not going to give you any false positive predictions. So that first example that I gave you was a test, with the one of the piece of paper that just says yes every time, a test with no specificity. It's not specific because it just tells everyone, that they have the disease. But just to describe a little bit more this sensitivity and specificity, here's another example in another article that I found, so you can read. I've posted this also on Blackboard to maybe improve your intuition about sensitivity and specificity. This is just a hypothetical example with type 2 diabetes, and a gold standard test requiring requiring long period of follow-up where you drink a glucose solution and then continue watching it as it is metabolized from your system. Whereas the screening test is just you fast and see what your background level of glucose in your blood is after you haven't eaten for a while. So, like I said, as is in general true for these things, the screening test is easy, fast, convenient, and more cheap, and the gold standard is much more difficult and expensive and time-consuming to do. So if you were to apply this screening test to, like in a case control study of 20 non-diabetics and 20 diabetics, what you find, and is generally the problem with screening tests, is there's natural variability of just about anything in the population. So even among the population of people without diabetes, there's quite a bit of background, or quite a range of the amount of glucose in your blood after fasting. So using that to test for diabetes is going to have some uncertainty, especially because there's also a range among those with diabetes, and these ranges overlap. That is where this uncertainty comes from. We're measuring something, in this case, fasting blood glucose level, and there's natural variability among both our negative populations and our positive population. So you want a yes/no answer from your test, though, and in order to do that, you have to set some threshold. So if you set a threshold of low blood glucose, what you're going to get is a lot of yeses. A lot of people predicted to have diabetes. So is that a sensitive test or a specific test? Does it have good sensitivity or good specificity? Well, okay, who says sensitivity? Who says specificity? All right, wisdom of crowds here comes through. This test has, if we set the threshold down here, it has better sensitivity than specificity. That means if you have diabetes, you have a high chance of getting a correct positive test. The performance is good on those with the disease. And if we calculate that here, there's 17 out of 20 diabetics get a positive test for a sensitivity of 85%. Whereas on the non-diabetics, we have not so good performance. We have 14 out of 20 of these non-diabetics being told they have diabetes for a specificity of only 30%. So what's going to happen if we move this threshold way up here to a high threshold? So keep in mind, I'm changing here an intrinsic property of the test. Okay, so that both the measurement of blood glucose and where I set this threshold, these are both intrinsic properties of the test. So that's why it changes the sensitivity and specificity, which are intrinsic properties of the test. So what have I done now to the sensitivity and specificity by making the threshold much higher? What's that?
Specificity increases in sensitivity.
Very good. The specificity increased, meaning that our performance on non-diabetics is better. We don't have so many false positives, but the sensitivity has decreased. We miss a lot of the true positives. We miss a lot of the true diabetics. And this is a trade-off. And it's a trade-off that unfortunately we cannot avoid without coming up with some better test, some fundamentally different test. Given the measurement that we have, this is a fundamental trade-off between sensitivity and specificity. And this applies across all kinds of prediction problems. Anytime you're trying to predict an event, predict an outcome, your predictions will face this fundamental sensitivity, specificity trade-off. It's like, I don't know, the trade-off between tasty and fattening or something. It's like, it's hard to avoid. If you get more of one, you get less of the other. Yes?
Or are there some tests where you can be highly sensitive?
So for this given test, it is exclusive and cannot be avoided. Given this just a measurement of blood glucose after, say, 6 hours of fasting, it is a fundamental limitation and trade-off. It is possible to get a better test, but it's going to require a different method, a different technology. So if you are being told that this test B is better than test A, you should ask yourself or ask the person who's telling you, how is it better? If it's just that it has better sensitivity, you should ask, well, is that because it has terrible specificity? Like, is it really better overall? You have to ask that question in relation to both sensitivity and specificity and how that trade-off occurs to say that some other technology is truly better.
But there are technologies that are highly sensitive and highly.
Yeah, there are technologies that are highly sensitive and highly specific. If it's an improvement in the technology. Actually, I think this trade-off comes up not only in diagnostic testing and such, but I think about all kinds of real-world problems in terms of sensitivity and specificity. Once you start thinking about it, you see it everywhere. So, an example could be is parole of prisoners. Okay, someone is in prison and they are released on parole. Parole is intended to try to release people who are at a low risk of recidivism, of committing another crime. But it is, of course, whatever methods they use are not perfect, and some people who are released will commit another crime. So, and when one person does that, you could think of that as a false positive. That person has been predicted to be safe to release, but then was not. And those things tend to have very, very high visibility. They get in the newspaper. They influence, they influence politicians. They influence public perception, etc. But it's just a false positive. And we actually don't have a measure of the false negative rate. Like, how many people are sitting there in prison without being released, even though they would have been safe to release? And in order to decrease that false positive rate, if you say it is unacceptable that we had this false positive, the only way, without some more accurate, prediction system, some fundamentally better prediction system, the only way to reduce that false positive rate is to increase this threshold, give parole to fewer people, and keep more, and create more false negatives, people who should have been released but were not. And in fact, the only way to get to a perfect zero false positive rate is just going to be to keep everybody in prison. So, so there are all kinds of things, many, many things that you can think of in terms of false positives, false negatives, sensitivity, and specificity. And if you remember that this trade-off between false positives and false negatives, or between sensitivity and specificity. It's a very fundamental property of probability, this trade-off. And if you remember it, you'll find it coming up in different contexts, completely unrelated contexts. But any time where there's a possibility of false positives and false negatives, you can think about it in this context and remember about that trade-off. Any other questions, comments before we move on? Yeah.
This just reminds me of a news I saw a few months ago.
Uh-huh.
I remember a group of a company said they developed an AI that can identify do fake news on news media. And they claim the AI is 99% accurate. So
Right.
it could be just it's being very sensitive.
So they claim they have an AI that is 99% accurate. And that is and that certainly is a claim that you're missing some information there. By way of example, if it turns out that only 1% of all news articles are fake news, or alternatively that 99% of them are fake news, you can achieve 99% accuracy using that trivial classifier, like our piece of paper that says, yes, you have cancer. Just a piece of paper that says, yes, it's fake news will be 99% accuracy if it's applied to 99% fake news. Or something that just says, no, it's real news is 99% accurate if you apply it to a news feed that only has 1% fake news. So that kind of claim is heavily dependent on the prevalence of fake news and on how you set that threshold. So whereas something like it's 99% accurate sounds great, but a lot of times when you just hear a basic accuracy claim like that, it comes from basically a case control study. Like half cases, half controls, you get high accuracy. That does not mean it's going to be highly accurate once you apply it to a real population with very different prevalence. So good example. Yeah, you will see things in the news regularly where you can apply this concept. So just to start giving some more idea of the complexity of a real-life screening test, in a typical population, there's no line separating these groups and they're mixed. So outside of our nice case control study where we knew they're 50-50, all we have is patients coming in. We don't know who has diabetes and who does not. So all we have is these measurements. And we know what our predictions will be, but we don't know what their accuracies are anymore. We can only know that based on our studies beforehand, where we did have these true labels. So in conclusion, different cut points in a something where there's a threshold to be set will yield both different numbers of predictions, whether it is like the number of people who are predicted to have cancer or have diabetes, or the number of prisoners who are predicted to be safe for release. Different thresholds of strictness will result in different sensitivities and specificities. Determining how many are considered to have the disease or whatever event we are looking at. And any cut point that identifies more true negatives will also identify more false negatives. So this trade-off either between sensitivity, specificity, or between true negatives, false negatives, or true negatives and positives. And a cut point that identifies more true positives, so less strict, will also identify more false positives. So these have all been what I call intrinsic properties of the test. But when we apply a test to a population, there are other considerations, because those measures of sensitivity and specificity were useful measures when we know already from some gold standard whether someone has the disease or does not have the disease, et cetera. It tells you about the accuracy on those with and without. But when you apply it to the population, what you're really interested in is, okay, I don't know what the answer is. I know what the test said. And based on what the test said, what is the probability of me having the disease or recidivizing, I don't know, or whatever else. And these are the positive predictive value and the negative predictive value. So positive predictive value is when you receive a positive test, the probability that you have the disease. And that is the thing that can really inform you about how worried you should be when you have a positive test. This is what you as a patient really care about. And you also should care about the negative predictive value, the probability that if you receive a negative test, you do not have the disease. So you see this is kind of in reverse of the sensitivity and specificity. And those we knew in advance whether they have the disease or not. This is more accurate or more relevant to the real world where you don't know in advance. You just get the test and it tells you what your probabilities of each event conditional on the outcome of the test. So whereas I calculated sensitivity and specificity among diabetics and non-diabetics, I calculate PPV and NPV among the positive test results and the negative test results. And the PPV is just the accuracy among the positive test results. So 7 people got a positive test, 5 were diabetic, so the PPV is 5 out of 7. And the negative predictive value is just the accuracy among the people who got a negative test, which is 18 out of 33 who received a negative test at this high threshold. And I think that this concept of PPV is really not well known, not only among the general public, but among healthcare practitioners and doctors. It's not well understood. And it, as a result, has caused great debate once patients and doctors realize that some of these tests that are very promising actually have not as good a performance as they expected them to in a general population. As I mentioned, prostate cancer, mammography, these are classic examples of screening tests that can be useful. They certainly give information, and a positive test increases the probability that someone has the disease they're testing for. But that positive predictive value can actually be quite low in the general population. So, and can result in a number of invasive and even dangerous tests and treatments. Another one I found, even far more suspect, TechScreen, a mental health screening program that apparently existed for a while that was supposed to be able to give a some written test to like high school students and then tell you if they have, I don't know, various mental health problems. Not good positive predictive value, and eventually shut down because it was identifying and causing a lot of kids who were just fine for their parents or administrators to think that they had problems that they didn't. All right, now I'm going to introduce you to some hardcore probability, just a little bit of it, but I want you to be familiar with it so you can perform some probability calculations that will allow you to calculate these things and understand how they're calculated. So if A and B are different events, such as, let's say, having a disease and testing positive in the screening test, then this is the union of the two, means either A or B. This is the intersection, meaning both. The complement is like not. So if A is having the disease, then A complement is not having it. And of course, the probability of something happening plus it not happening is always 1. So if you have the probability of something happening, then 1 minus that probability is the probability of it not happening. And finally, this is what we call conditional probability, which sounds scary, but we've been talking about it all along this class. And it's the probability of A conditionally on B being true. So it's the probability of having the disease conditional on receiving a positive test. It's the probability of receiving a positive test. If you have the disease, it is the probability of something when you already know something else. That's all it is. So these are what we call Venn diagrams, and they're just a visual way of demonstrating some of these things. So if A and B are 2 events, then the intersection is this intersection of those 2 circles. With 3 events, say this could be cancer, diabetes, heart disease, this is the very unlucky intersection of having all 3, and we have some lesser unlucky intersections of having 2 of the 3 diseases. And this would be the area of only having 1 of the disease. And outside of here would be none of these events. So typically you'll see these written in terms of numbers. Like if you have known probabilities or numbers from a study, you would write how many or what the probability of each of these areas is. And it's a way to communicate these probabilities without actually having to write them as probabilities and in a more visually intuitive way. So maybe I'll just go through a couple of these just to get you warmed up. You'll have more of a chance to do this during the lab. But this first one, so this is event A, this is event B, and I've shaded this area in B. How would I write this down? What is this probability? It's not a complement because it includes some of A. You could do it that way. The simplest way to do it is it's just the probability of B. But you can ignore A here. This is indicating the probability of event B occurring. You're skipping ahead like to 4 here. So here is something that involves both A and B. This is going to be hard to write on here, but so this I'm going to write as the oops, probability of B this is the probability of A and the complement. So it has to be A and it has to be not B. This one? Sorry? A union B. Excellent. Or in other words, A or B. This one? Yep, just probability of A. There are more complicated ways we could write this, I think. Although I don't know how we would involve B in it. How about this one? Probability? Yeah. B and A complement. Very good. And finally, A and B. Excellent. A and B. So you can already see how these probabilities are going to enter into some of those calculations. Like if you want to talk about, oh, I don't know, let's see. This is the probability of A and B would be like, let's say, the probability of a true positive, when you don't know in advance whether someone has the disease or what their test outcome will be. It's the probability of receiving a positive test and having the disease, not a conditional probability in that case. That's like the probability before you know anything, before you walk into the doctor's office. This is the probability that you're going to go in there, you're going to receive a positive test, then they're going to do follow-ups with the gold standard and find out that it was truly a positive, that you have the disease. This could be something like a false positive. The probability that you're going to go in, you're going to receive a positive test, and then you're going to find out that you do not have the disease. Mutually exclusive events are things that cannot both be true. So for example, having chlamydia and not having chlamydia are mutually exclusive. Either the infection is present or it is not in an individual. And these are non-overlapping Venn diagrams. And in these cases, the probability of the union is just the sum of these two areas. And in this example, where they're exhaustive, there are only two possibilities, then the probability of that union is also 1. Meaning that the probability of having or not having the disease is 100%. There are no other possibilities. And the probability of both is 0. There's no intersection between these two events. When we have non-exclusive events, such as having chlamydia and having heart disease, then there's an overlap. There's an intersection. And in this case, the probability of the union is the probability of one event plus the probability of the other minus this overlap, this part that's getting counted twice, the intersection. And that intersection, the probability of both, is just the product of these two if they're independent events. So if having chlamydia and having heart disease bear no relation to each other, then the probability of both is just the product of the two. Just like probability of flipping heads on a coin twice in a row, assuming they're independent, is a half times a half. Conditional probability, we write this way: the probability of event A with this bar that means conditional. Conditional on B being true, or B having already happened. So for example, the probability of having the disease conditional on receiving a positive test, the positive predictive value would be written like this. And that is this intersection area, but then divided by the probability of the thing that it is conditional on, because we have to assume that it has already happened. So the positive predictive value of a test could be your probability of having the disease conditional on receiving the positive test, or written another way, it's the probability of both things happen divided by your probability of receiving that positive test. And Bayes' rule is just an expression of this conditional probability, saying that the probability of A and B is the same as the probability of B and A, and expanding on that thing we had on the previous page with this commutative property. And it gives us this thing, which you don't have to derive it, but you should be able to make calculations based on it. That in order to calculate the conditional probability of A conditional on B, you can do it if you have the other conditional probability, B conditional on A, and both of these probabilities. And you're going to use this for doing things like, and you'll be allowed to use a calculator and a spreadsheet formula and everything for it. But given the sensitivity and specificity of a test, so this probability of B given A could be the sensitivity, and also given the prevalence and both the probability of let's say a positive test and the probability of having the disease will allow you to calculate the positive predictive value. It'll allow you to go back and forth between sensitivity, specificity, and positive predictive value, PPV, and negative predictive value, NPV. That's the main use of it for you. So you've all learned lots now. Answer this question for me. Does the probability of A conditional on B equal the probability of B conditional on A? No. Very good. I love you're that confident in it. Good. If you've learned one thing from this class, that can be it. That's only the case when the probability of those two things are identical. So for example, the probability you would retire, given that you had as much money as Trump, is not the same necessarily as the probability that you would have as much money as Trump, given that you've retired. So they're just not comparable. How are we for time? I'm going a little, I guess we have a little more time. So let's go ahead and calculate a few things here. Back in lecture number 1, we had this example of the pain study with treatment and control groups and self-reported pain on a scale of mild, moderate, and severe. So what is the probability of being in the treatment group here? The probability that your group is treatment. Here are our numbers. What's that? 50%. Very good. 0.5. The probability of reporting mild pain, the probability of pain equals mild. 0.2. Very good. Okay, now we've got a couple of conditional probabilities. Scary. The probability of mild pain conditional on being in the treatment group. What's that? So let's look at this treatment column. I can't see my cursor. Okay, there's the treatment column. So it's conditional on being in the treatment group, which means we're only going to look at this column. And the probability of experiencing mild pain is 15 out of 50, so 0.3. And the probability of group equals treatment conditional on pain equals mild. What's that? Sorry? I heard 15. 15 out of 20. So the if you experience mild pain, you have a 15 out of 20 probability of being in the treatment group. So it's 0.75. Yeah. So the probability of being in the treatment group conditional on pain equals mild. This is like asking, okay, of all of the people who experienced mild pain, it's conditional on having experienced mild pain, what is the probability that one of those people was in the treatment group? And the probability of them being in the control group is 5 out of 20. So there are 20 people who experienced mild pain, 15 of them were in the treatment group, and 5 of them were in the control group. Any questions? Okay, this is maybe getting a little too, a little bit too much math for the class, but you can take a look at this if you're want a few more examples of calculating these different things. All I am doing here is taking this table and these marginal totals and calculating the prevalence, the sensitivity, the specificity, the PPV, positive predictive value, and NPV, negative predictive value. And given this sensitivity and the prevalence in the population, you can calculate the PPV. So you can take the sensitivity from a case control study or from one population and apply it to any other population using this Bayes rule formula. And if you're scared about that, I'm even going to let you use a Bayes rule calculator. This is online. You're allowed to use it. You enter this actual probability is the prevalence, probability of true positives, false positives. As long as you know what these things are and you're able to calculate them, like the true positive rate, the false positive rate, the prevalence, you can just use a calculator like this. I'll also provide a spreadsheet with the formula in it for you, so you can just enter these things and do the Bayes rule calculation. But you have to understand what some of these basic things are: how to calculate prevalence, how to calculate true positive rate, that's sensitivity, false positive rate, that's specificity, and then you can use Bayes' rule to get all of these useful, interesting things like PPV and NPV. So in this example here, I took this same test, 98% true positive rate, 3% false positive rate, and applied it to that STI clinic with the prevalence of 30%, and got that PPV result that I calculated before of 93% and of 50% when applied to the lower prevalence population. And nice thing about the calculator is you can start playing around a little bit and ask some questions like, what if this test had 100% sensitivity, like it never missed an infection, never missed a true positive? This is an important example here, and I want you to remember it. I might even ask you about it again. Where we have a test with a low PPV, and it has some limitations in its false positive rate. What happened to that PPV when I increased the sensitivity, the true positive rate, to 100%? What's happened? Didn't affect the PPV. It didn't help. That's a really important thing to remember. Why didn't it help? So, you know, in this class, I really don't want people getting lost in the formulas and lost in the math, but I really want you to come home with an intuitive understanding. You know, doing the practice that you'll do in the lab and the assignments, they'll help with that, but I want you to have an intuitive understanding of some of these things. That the positive predictive value, if you're in a population with low prevalence, is going to be dominated by the performance on those negative cases. If you're applying it, in this case, to a population where 97 out of 100 people do not have the infection, then if you want to improve this probability of having the disease given a positive test, well, you really have to improve its performance on those negatives. It does not help you getting 100% on the positives. So I'm going to put a big like star here, because this is like, I already know, like, we're going to ask you about this again, and a bunch of you will have forgotten that if having a poor PPV and increasing your sensitivity to 100% does not help. What will help? If we need to increase this PPV, what will help? What's that? The threshold? How would it help? How can we improve this PPV? You're right. You could improve it by changing the threshold. How? Well, the problem with if you increase the threshold, let's see. So by increasing the threshold, you increase its specificity, right? So you're right, that would help, because you're going to improve its performance on the negative cases. So that would be one way of improving the PPV. You're going to give fewer people positive test results, but those who do, you're more confident that they have the disease by increasing that threshold. If we had a better technology that kept the sensitivity the same, let's say, while improving the specificity, that would also help. In both those cases, we're improving the false positive rate. So they would help. What's one more thing that could improve the PPV of this test. We've only got 3 boxes here, and I've talked about 2 of them already. So increasing the true positive rate to 100% did not help. Lowering the false positive rate, yes, that would help. What about this other one, the actual probability or the prevalence? Yeah.
Increasing the prevalence will help because it will give you a better chance of predicting who actually has the.
Yeah, outstanding. Applying the same test to a higher prevalence population will improve the PPV. And that's why we have some screening tests that are approved for high-risk populations and not approved for lower-risk populations. So remember those things. Okay, wrapping up, the probability of having a disease given a positive test does not equal, and you all know this now, the probability of a positive test given that you have the disease. Those are opposite conditional probabilities. They're not the same thing by any means. So when you hear something like accuracy, you need to think to yourself what you're actually talking about. Is this like the accuracy for people who received the positive test, or is it the accuracy for people who have the disease, or what is it the accuracy for everyone? If so, what was the population it was applied to? But you need to understand these concepts of conditional probability in order to understand any of these claims and performances of a diagnostic test. Remember that sensitivity and specificity are intrinsic properties of a test, whereas PPV and NPV are applications of the test to a population. This is a useful slide just because it puts everything on one page. Even I sometimes, if I haven't thought about this for a while, need to be reminded that sensitivity is the same thing as true positive rate and specificity is the same as true negative rate. So it's useful to have this as a reference. Here's a quick cheat sheet of the notation that we've done, and I'm going to wrap it up. Are there any final questions before we take, let's say, a 10-minute break and then go to lab?
Can you repeat what improves the PPV and should improve specificity?
Oh, yeah. So what improves PPV? Applying the test to a population of higher prevalence, that can improve the PPV significantly. And improving the specificity or the false positive rate, that can help. Its performance on the negative cases, that can help. But improving its performance on the true positive cases is not going to help the PPV. Welcome. Thank you for asking. That's a point that I want to drive home. All right, so it is 6:20, and I'm going to sign off, and we'll switch over to lab.